Okay, we are live. So anyway, for this very small community today, I'm going to basically the talk is on a new way to look at Maxwell or to look at electromagnetic waves. Now I must just find the button to share my screen. Here it is. It is there. Share. Okay, so welcome. That's just the title. And the first question I asked, what is a wave? And the best definition for a wave I found was given by Dudley Town in his actually opening statement of his book, which simply states if the mathematical representation of whatever leads you to the what I call the D'Alembert wave equations, which is a second order differential, which you see here, which was proposed by D'Alembert in 1748 in the one-dimensional form, and a decade later Euler presented the three-dimensional form. And this is the only wave equation that we know to date. Of course, there are derivatives of this if we would think of the Schrödinger wave function, etc., etc. I'm just a recap on the basic reference system. If I've got a x, y, z coordinates, and basically these unit vectors for x, y, and z are defined by the dot products of any two vectors being 0, and then being a right-handed reference system, we have x cross y equals z, y cross z equals x, and z cross x equals y. And if we look at that, we've actually got a sequence, because what have I done? I just rotated the x to the end and moved these two onto the left-hand side, so the sequence carries on forever. So basically now let's define three vectors: a velocity vector, which has got a scalar and a unit vector in time, an activator, which is again a scalar times a unit vector in time, and a reactivator. Basically, they're all orthogonal to each other. Therefore, the dot product u dot a equals 0, a dot I equals 0, and r dot u equals 0. But if we look at the cross product, we have a infinite sequence. Now, the sequence, it suddenly occurred to me, I can renormalize the sequence so that...
Sorry, can you explain how the infinite sequence arises from the cross product?
Okay, let's go back to here. Thank you for interrupting. You know, if anything is not understood, please interrupt. We've got lots of time. If we look at the sequence here, x cross y equals z, then I just move the symbols, rotate them to the left. I get y cross z equals x. I rotate the symbols to the left again to give me a z cross x equals y. And then if I rotate this left again, I'm back to this point here, okay?
So this is the infinity of the handedness of the coordinate system. The fact that it's right-handed, so it can turn right-handedly infinitely.
Correct, Laurie. This is exactly what it is. But as soon as I put a scalar into it, that the scalar CA and R to the unit vectors U, A, and R, this sequence now is indefinite, because it is, although the orientation is correct, the values either grow or collapse into nothing, depending on what the values of A and R are. So if I now normalize them, and I can, the sequence now carries on forever. So if I have R equals U cross A as the first one, and then U equals A cross R, basically you see I still do the rotation of the symbols as I did earlier. But if we look at R, I've got a UA, so I've got basically a squared U on the top. And so I divide by the A squared again to bring it back to U. And then similarly here with the last equation was A equals 1 over U squared R cross U. And the solution of these three simultaneous vector equations describe what are called bimodal, bimodal transverse waves. So this is the innovation that I'm presenting here today. It's very simple, as such. Now, now let's map A to B, the magnetic field, and R to E, the electric field. This is just, I'm basically setting this now into the electromagnetic domain, but I know nothing about what the electric field E and the electric magnetic field B are. I just put them in there, and I basically have these the same three equations here, and activation by B, this I call vectoring, and then reactivation. Basically, activation and reactivation is equivalent to self-inductance. Here I basically describe what these what they are, so that the velocity vector is c times a unit vector, and the unit vector is a function of time only. The same for the magnetic field, and the electric field is given by this equation, so the same. And then I've got the position vector, which is the position is the integral of u dt. So if we now look at how these vectors relate in space, I've got my reference system x, y, z here. I've got my position vector and the three vectors that make up the MUBE, the set of equations. Now, here I'll repeat what I've done earlier, and basically I'll make the statement that the equation set MUBE predicts the Maxwell equations. Basically, it is superordinated to the Maxwell equation. That's a very big word for me to say, to superordinate something over Maxwell, but I will show you why this is true. I'm going to perform a left-hand, right-hand curl, in other words, a curl on the left-hand part of the equation and a curl on the right-hand part of the equations. I'll go back here. A curl E equals a curl U cross B. And basically, I need to find I come up with these two, and I need to evaluate the analytical expansion of the triple vector product. It is basically the, what do you call it, the Bagh-Cab rule, but it's again repeated here. And the reason why it's repeated is that it is the I've got a product of two functions. So basically, it's a product. If I do a differentiation of a product of two functions, it is what's it? G df dt plus f dg dt. So this is basically exactly what we're doing here. Now, what do these evaluate to? Very simple. Most of these terms are all zero because the gradient of u, the gradient being the partial of partial derivative of x, a partial derivative of y, and partial derivative of z, with the dot product of u. And because ut is only a function of time, it is zero. So basically, all of these are zero. I have the same here. I just had to think about it. We basically expand the dot product of b cross the grad or gradient or nabla or whatever we want to call it, which then gives us this part. And then I've got a CUT over here, and that is again zero because there are no x's or y's in that equation. It basically also means that in the vacuum that the as in the derivative in deriving the normal de Albert wave equation is sorry, I mispronounced it, the Allenbert wave equation. We always say that the speed of light is independent of position. So I've got these two terms are also zero. Now, what are these terms? The velocity times the gradient multiplied by b and multiplied by e, and this is a simple partial derivative of t, because the velocity, if I expand this term, I have a dx dt times the partial d dx and the partial divided t, etc. And this all basically is simply d dt. So the triple product of the gradient ub is minus the d dt, and the triple product of the gradient of the electric field and the velocity is the e dt. And if I show it to you here, I now have the Maxwell equations as the curl of E equals minus dB dt, and the curl of B equals 1 over c squared dE dt. We've already established that the divergence of B and the divergence of E is zero. And these are the Maxwell equations if we can prove that 1 over c squared is equal to epsilon 0 mu 0. So, but basically, I now have shown how the simple of those three algebraic equations have formed have given us the Maxwell equations. So, and because the Allenbert wave equations are derived from the Maxwell equations, I can say that this is the solution of this set is a wave equation, because basically the functions of t describe the wave according to time. So basically, these three simultaneous equations lead to the Allenbert wave equations as such. So basically, this I call is a wave equation which I call the bimodal transverse waves. The next step is to show that MUBE, I used M to honor Maxwell here, by the way, that it is the Maxwell equation, not by simply substituting c squared equals 1 over epsilon 0 mu 0, but we take a more difficult path. We make, I make two assertions that an elementary electromagnetic wave exhibits power or h over t squared, h being the Planck constant and t is 1 second. This requires B to be an elementary field of both. And then I make the second assertion, I make that an elementary wave transports an electric charge E every 1 second as a wave current. This is nothing new. This wave current is exactly the same what Maxwell described this as a displacement current. And if we think about it, your radio transmitter, the power that goes into the transmitting that signal, when you receive it in the area, induces a current. In other words, energy is being transported from the radio transmitter to your radio receiver. So this assertion is very supported by experience. Now, I basically the equation which are called vectoring, this u equals 1 over b squared b cross e. I make take the premise that this is indicative of wave action, which is actually the Poynting vector, but it is of opposite sign to the Poynting vector. In the paper that are on the internet, I actually point this out, and I think that I looked into the derivation of why it is the Poynting vector should be S equals E cross H. It was an arbitrary choice. There was no, and I basically in the paper I'll show that I won't go into it today here. But anyway, we multiply this then by H, and we take the look at the norms of it, so that we get H equals H over B squared, and the product BE. I then bring in an additional step, and that is multiplying it by an elementary distance, where the elementary distance is c times t, and basically multiplying and dividing it here. Now, the square brackets here indicate that I'm developing a constant, and I want to eliminate basically b in here and express this in terms of h, e, l, and c in the fundamental units. So now I define a elementary electromagnetic action, h sub e equals rho h, where rho is just a conversion of 1 coulomb per kilogram, just to keep my get my units correct. And we know action is momentum times distance. Therefore, I can say HE equals kappa LE, and the product of LE and C. Kappa is basically a dimensionless proportional constant of unknown value at this stage. Because I don't, don't know how, I can't say I need to bring in a coupling constant or a proportional constant here. I can also say that the or postulate that electromagnetic action is proportional to the product of the magnetic field B and the elementary volume which the wave occupies. And again, proportionality constant chi L cubed times B. So I don't think you've got, I hope you haven't got any problems with these definitions that I bring into the field here. Therefore, we now have the electromagnetic action H sub E equals kappa LEC equals chi L cubed B, which gives us B equals kappa EC over chi L squared, just by rearranging the terms. And we substitute this B into here, which gives us this equation. But we know that E equals CB, which we now introduce in here, which gives us this equation here. It's simple substitution, nothing fancy. So repeating that equation here, we can now define what B is all about. And I say B equals H divided by L squared, or rather by kappa L squared and times the electric charge. But that is only true if 1 equals this equation, if this evaluates to 1. So now let's just look at this. We know that we've previously defined B equals H over kappa L squared E, which we substitute in here, which equals 1. That requires 1 over chi to be the inverse of this, with the factor with the c here to cancel out the c squared, and this is basically all that remains now is to say, well, kappa squared is 1 over 2 times the fine structure constant, and I now have epsilon 0, mu 0 defined completely out of mathematics without a single measurement of what Faraday and all the earlier pioneers did, that Maxwell could, or basically it was Faraday, I think, who discovered, Coulomb defined epsilon 0, and I think Ampere defined mu 0. So the only, if I didn't know what the fine structure was, we would have stayed at mu 0 being kappa squared E squared over HC. So basically, now having defined that, having obtained epsilon 0 and mu 0, which is the way that it is defined now at NILST, and how basically defined from the work that Sommerfeld has done. And basically with this, I conclude that that MUB ER is a reformulation of the Maxwell equations. So if we now look at the fine structure constant, if we read the website of NIST, the modern view also includes that it's a coupling of electromagnetic force to the other three forces, being the small gravity, the is it the small force or the weak force, and the strong force. But if I bring out here, I now have kappa equals 1 over 2 alpha. So for me, it is a coupling constant of electric momentum to bring it into the to couple or basically to scale the electric momentum so that it scales equally to the mechanical, sorry, let me repeat, the electrical action scales to the mechanical action. So we've got a new way of looking at the fine structure constant. Now, what if? You know, that's a nice question one can always ask. Oliver Heaviside presented us with a vector algebra that I used. Planck proposed the quantity H in the year 1900. Millikan published the electric charge to within 1% to what it is now today in 1913. And then I say, what if Heaviside presented us with this equation set, which you very easily could have done? Well, we would have a Heaviside constant of 8.277. The magnetic permeability, which was a fixed value till only a couple of years ago of 4 pi times 10 to the minus 7, would have been expressed in terms of these constants. And then in 1916, Sommerfeld would have established that the ratio of the fine structure constant to kappa squared. And all the magic and discussions if the fine structure constant, you know, is a fixed, and you know it is all would never have happened if we had this a Heaviside constant. But nonetheless, if we look at this equation of rho h equals kappa LEC, we now can establish we use the Heaviside constant, which are called and an elementary length and an elementary time of these values, a lot smaller than what the Planck length and the Planck time are, but in view of what I've done here are fairly elementary values. The magnetic flux quantum is defined as the Planck constant divided by 2 of the electric charge. I have no problem with it. It was observed experimentally for the first time in 1961, and Shankar shows us how to derive it by analyzing the Aronoff-Bohm effect. So, you know, that we cannot argue that this value does not exist. You know, it is there. However, if I take the magnetic field being H kappa L squared over E from my equations, I get a elementary magnetic flux in the as H over kappa E, which is very much smaller than what the magnetic flux is. I don't want to put any quantized nature into this, other than that when I express it in the pointing vector, in this, use this value as in the elementary form, I have it works out correct, which basically confirms the first assertions in slide 15, where I say that a elementary wave carries an elementary, has an elementary action. One of the questions that comes out of this is, what is the meaning of epsilon zero, mu zero? For me, up till I did this work, it always defined the velocity c of the vacuum. But I have now shown this or derived this in a mathematical way, so it cannot be in my opinion, it does not define the speed of light from first principles of what the vacuum is. I thus propose a transportivity of space being c squared. How to define it, I've got no idea. If we look at fluids, in the fluid, the velocity of a sound wave or a pressure wave in fluid is given by the coefficient of stiffness of the fluid divided by the fluid density. Alternatively, we could also express it as the partial derivatives of the pressure and the fluid density. But I must take note that none the coefficient of stiffness, the density, nor the pressure has got terms of are defined in terms of c. Therefore, I think there is something else in the vacuum other than epsilon zero and mu zero that defines the speed of light. That is all I can say at this stage, and I wouldn't even try and attempt to define it. It is just an open question or proposition that I've put in there, as I said, yet undiscovered, which are not functions of speed and light. Describing electromagnetic waves. So we can use these, basically need to define these unit vectors, which basically, we're repeating here again what we've done earlier. Just want to, the slide, I say that the wave is described by m, which is parameterized by p. So if I now use the equation, the wave parameterized by p, I imply this statement here, and that the vector p is the integral of u dt. It is just a short, this here represents a short form of this here. Now, normally we describe electromagnetic waves in terms of phase velocities in this way. Now the phase vector k, the product of the velocity vector, what would you call this? The phase velocity vector kn times the distance reduces to this. This equation is normally not shown because we always use this equation, but as such. But let's leave it at that. Now, if we look at a single plane of an electromagnetic wave, I can basically the velocity, the I plane of the traveling plane wave, I can define as moving along the z-axis, I can define as z, the vector z, the unit vector z, the initial position where we started off at time 0 plus ct, so that this is easy enough. And I, putting this into the parameters, I have the velocity is in the z direction c, and b and e take on these forms. The cross it has to be in this form so that the cross products, those three equations, that they all work out. These two values here, it's nothing more than the first rotation or in an Euler rotation. So, but why? Let's see. So that I now have the ice plane, and I say, why do I need to have it as complicated as with these terms here? We know what pi is because we've evaluated it there, and it just simply comes down to the traveling plane to a parameterized to values without t. They are just all fixed values, and this is basically what a radio wave looks like. This is where it gets interesting. In the paper, which you can find on the website, I have the show a wave as a torus. I'm skipping it here, and I will now just do the example on the ball lightning. If we have a traveling object and we define the unit vectors as x sine omega 1 t sine omega 2 t plus y, these are etc. These are the basically normal spherical coordinates of a system. If I integrate it, I now get the path of the wave as expressed in these terms here. The path is closed. It has a path length of 2 pi c. I will show you pictures of these paths later on. And if I now define a soliton or ball lightning in terms of these, which has this spherical, basically travels along this path here, are parameterized by this. All the cross products work out. You know, I've done this all in Mathematica. If anybody's interested, I can give you the Mathematica software that you can play with it as well and look at it. It's these are just simple Euler rotation. It's these terms you'll find you can pick up in any Euler rotation matrix system, so it's nothing fancy, and they have to be that so that these are all co-orthogonal. So, and basically because these satisfy these equations, and we know that these equations lead to the wave equations, then phi pt describe an electromagnetic wave propagating on the closed path S0 at the velocity c. The interesting part is this part here, the magnetic field, which forms a circle. This is what's keeping the wave together. If I can think of just two planes on the opposite ends, they will have basically they all share this common magnetic field which then tightly holds us together in a circular form. If I look what this looks like, this is looking down on the North Pole, and this is a sort of isometric view. The large curve is for omega 1, omega 2 is 1 and 2. This triangular one is omega 1 to omega 2 is 1 and 3. And this smaller one here is 1 and 7. To understand this curve, if you take two of them and sort of turn them 90 degrees, they fit exactly into each other, which is nothing more than a baseball curve, or that a baseball is made out of two halves of leather instead of a cricket ball which is sewn together of two semispheres. The baseball is sewn with a leather piece that looks like this to give and stuff to with each other. The interesting thing, when I looked at this, I immediately, what came into my mind is a pecking order of electrons. We have the first orbit being 2 electrons. The six here are 2 electrons. This one here, which has 3 multiplied by 2 is 6 electrons. That is right down where uranium sits. I haven't drawn the one with 5 in here. This is what immediately came into my mind here. So basically, if one looks at the people who have studied ball lightning, Arnulf, Chupicalo, and Cameron are the ones that are mostly cited. If one looks at these papers, they all construct 3-dimensional waves using superposition, whereas in my case, it comes out of those 3 equation set. Basically, now, if we look at the definition of a solitron, it represents a wave of permanent form. It is localized, can interact strongly with other solitrons and retain its identity. That the last of basically 1 and 2 are satisfied. 3, I hope to show at a later stage as such. So basically, here was I conclude my talk. I say these bimodal waves, I use a German word aufschlussreicher. Aufschlussreicher basically translates to enlightening, illuminating, informative, insightful, instructive, revealing, and telling way. What is remarkable that I've now just taken mathematics and have derived the Maxwell equations in vacuum, which are at the heart of physics and quantum mechanics and everything, without knowing anything about magnetics, so it is a complete mathematical derivation of the Maxwell equations. So when I said earlier that these 3 equations, that equation set M, that sits or is sits on top of Maxwell, I'm sure I'm not wrong there. Thank you for listening. Let's discuss this. Okay, open for questions. Let me put. Quiet. Laurie, you had a question initially.
Yeah, well, what immediately springs to mind is that surely from this there is derivable and an empirical experiment that could be set up to create a standing wave to demonstrate this soliton waveform. So, if we can create in the laboratory something like ball lightning using this formulation, that would be a strong confirmation. Can you speak to that?
Ball lightning, I think Nina knows more about this. I think the people who really studied ball lightning are in the Russian laboratories. It is difficult to set this up. Okay, if you now know this, maybe one can construct antennas to direct this.
Well, what I'm claiming, what I'm suggesting is, by analogy in fluid mechanics, where we have a model in which we can produce a soliton form, then we can create apparatus that will manifest it. So where we can have control over the electromagnetic fields through some physical system, we should try to see if we can proceed from the mathematics to imagining constructing an apparatus that would be able to demonstrate the soliton.
Let me just show you something. Let me just get something up on the internet. Possibly. Oh, come on. Let me just make this a bit smaller so that you can see it. I'm just setting up a screen sharing at just a moment.
Or if not, one could at least try to theorize bounds for the energy levels that we require to meet the condition of wrapping around itself to make the
I'll show you something now. So
there's presumably there will be some bounds derivable.
Yeah. This is a recent photograph published just a month ago from NASA. It is called the WR40 is the correct description of it. They talk about shells. So these are sort of shells around it. It is the explanation that they give. It's a binary star system that when these stars get together, that the solar wind of these two stars sort of blow the dust off the sky into these shells. These shells are hydrocarbons. So how you get hydrocarbons out of a sun, I wouldn't know. The Nature article is quite interesting. It's you can see it here. And now I'll show you a photograph of taken in the laboratory. This is the Sapphire project. It's a Canadian crowd. And I don't know what the status of the project is now. I was in contact with one of the scientists of the project. They basically run out of money after spending $10 million. That whoever funded them, they've stopped funding them. But what we have here is we have a steel anode in the middle in a partial hydrogen vacuum that has formed these spheres around us. When I sent this this picture to my contact in that project, Michael, what's his name? Michael Clarage, I think his name is, I sent him this Nature article. So it's no longer available. It's basically Nature for the first months. You can see. Sorry, you had access to it. I don't know if I kept the PDF file of it.
I can access things.
Yeah, but if you look at the telling figure in this article is they take the spectrum. They have some unidentified infrared spectrum in this ring, which basically show the difference to the spectrum from here to there. So something is exciting this for it to radiate Now, if I basically in later articles, if one basically scales us all up to these astronomical scales, could that be described by the equations? I don't know if you do some research on the Sapphire project, they've got some fancy videos. I can try and find them. By the way, if you want reference to this, you just Google the site Harbingers of Neophysics. This is a site that basically it's under this what I've started here now. This is what I do. You can find this under blogs.
Mm-hmm. Yeah, no, I've got the
and if you can open the Nature article and then if you look at the way that they describe this, but it's a figure 5. Let me just get up the email of what this guy's written back to me while you do that. If you want to share your screen, let me just stop share, and I must do here. All participants. Okay, I think you can share your screen if you've got the article. If you want to show that figure 5.
I'm still trying to. I need to. Yeah. I need to.
But let me open up my email system and just to give the comments back from Michael, which were quite he was very excited about
there's a preprint on ArcSID actually.
Oh, is it preprint? Oh, good.
Yeah. I'll post the link in the chat. Hold on.
Yeah. Now, Michael writes, my comments on the model from Lau et al. The model explains things okay. It is based entirely on gravity, dust, and gas. The production of dust seems like a fair amount of hand waving. This is a weakness since the observed radiation is coming mostly from this dust. Hydrocarbon dust created from 2 solar winds crashing into each other from stars that have enough carbon spewing off. What about the other elements that would also be present if you had this much carbon? I see no ballpark calculation on whether or not solar radiation would excite this dust sufficient to produce this observation, and not at the time excite various other stuff which we do not see in this observation. Why are we referring to hydrocarbons as dust? the existence of hydrocarbons in space is a profound mystery. Why not say that we are seeing many of the molecules we previously thought only existed on Earth, which molecules only exist because of action of life. Perhaps we have no clue how these compounds arise in space. Figure 5, I was excited. This is now what I talked about. Figure 5, I was excited about, but it seems they are not presenting the data of the gap. The gravity model assumes that the bright rings are carbonaceous dust grains, while between the rings is just the sky behind. But the electric model would say the entire region is the atmosphere of the system, while only the double layer regions are excited. Now, when he refers to double layers, is what we saw in the anode. I want to see the raw data from the gap. They seem to have just fit a smooth curve and hence thrown out a lot of the interesting stuff.
I can show you figure 5 if you want.
Yeah, it's
Can we come back to the more general things away from ball lightning?
yeah, but it's just on the question how to produce it is basically, suddenly occurred to me on the Sapphire project, because there are other observations that they do where they have actually very much smaller little balls. I must try and find this video and show it to you. But anyway, Mike, carry on with your what you want to carry on with and ask questions.
Well, where do you feel that your argument is weak or needs some help? For example, in Peter Rowland's work, he has space as a fundamental notion. Are you, in some sense, changing the meaning of space there? But my more interesting question is where you were trying to explain or to use the theories to do with sound, and you ended up saying there are some, if you like, features to be explained there. If you like, the fluid, the basic fluid, maybe shortly after the Big Bang or something, you were trying to characterize that, right?
I basically, I don't know. It is. I'm thinking about it. I'm taking a completely mathematical point of view. And I will develop this further on. I will, in the next talk, I will do particles using these equations, and show that they are particles. And then the third talk on that is basically I will extend the particles to show that they can interact, or why they can interact. Exactly why from the mathematical point I don't know. If we think of of space, it's basically the term that we're not supposed to use is the ether. But there is something there that the electromagnetic waves can travel in, or the particles can travel in. And particles have to be waves as well, in my opinion.
You're expanding the notion of the medium in which the wave disturbances arise to have some more characteristics than in the minimal interpretation of the Maxwell's equations. Yeah,
correct. And how to measure that, I've got no idea. If this measurement can come out of experiments like in particle physics, why we have these the particles, or the fundamental particles at those particular energies, maybe there's a clue in there that I would have no.
I found it interesting that you were changing the emphasis or the relative contributions of what goes in, like the permittivity and the two constants at which you get the speed of light, saying that it's arbitrary that we kind of landed on a particular. It's not arbitrary, it's a result of the history of the development of it. Had it gone another course, it could have had a different construction, and therefore we would have had a different understanding of what the fine structure constant is. And I think it's quite good to explore what that means theoretically. What we have closed for. We might have foreclosed upon ways of looking at things by reifying a particular constant. Where we might have reified a different sort of collection of properties.
Correct, Laurie. Look, for me, the astounding thing is that I used mathematics to derive the constants. Okay, I introduced in the end, I introduced the measured fine structure constant, but it shouldn't be, in my mind, possible to define those constants from pure mathematics. That's from basically what I've done. I've taken mathematics and I made two assumptions. Let me read these assumptions again. That's where are they?
Well, while we're on the fine structure constant, you pointed out the modern idea is that the fine structure constant isn't only related to electromagnetism, but all the other three, allegedly four forces, which go as for some reason in a group, right? Now, I don't know if that was hand waving or whether you are happy with other people who've made that connection. That I don't know if you know, but a certain Clive Kilmister spent a large fraction of his ANPA time worrying about the fine structure constant. And I'm wondering if you actually use the mathematics to calculate a number, whether you agree with Clive, who was very unhappy that it wasn't a whole number.
I'm not. I replaced a kappa squared constant with 1/2 alpha to make my expression or the pre-expression or these two constants that are developed equal to the formulations of epsilon 0, mu 0.
Yeah.
That is so.
I thought that was a neat move.
It is nothing more than what any theoretical physicist does. He takes a measurement and puts it into his formulas. So it is basically, it was just that measurement of known fact that I put in there. But other than that, I shouldn't be able to basically put down a mathematical equation, make two assertions. Assertion one, that a wave exhibits power h/t squared, and that the elementary wave transports an electric charge E every 1 second as a wave current. Those are the two assertions that I make, and with those two assertions, I come to epsilon 0, mu 0, from purely mathematics, where other people spend, the expressions that I put down are the expression of Sommerfeld. He was the one who basically defined the fine structure constant in terms of electric charge, the Planck action, and c squared, or c. He basically, and from that, and from Sommerfeld's, or I should rather say Sommerfeld work, we now have the modern formulations of mu 0 and epsilon 0 as are derived mathematically.
I'm very happy with your approach. I'm very happy that you may have removed one of the 17 constants which have to be put in by hand. But I'm still interested to know where you personally feel that you were doing a bit of hand waving.
I have not done any hand waving.
Okay, all right.
You know that I haven't done any hand waving, but the only hand waving that I've done is these two assertions. You know, where I say a wave exhibits power h over t squared. Every wave has power. We can see this when there's a storm blowing in the sea, and that the wave transports an electric charge, which is also not hand waving because that's what Maxwell has said.
Okay.
You know, so I've got no hand waving in there. I'm completely sound with my mathematics.
Have you considered? Sorry, I was just going to ask. Have you considered? So one of the things I always think about is the you know, I was concerned. What's the experience of a photon traveling at the speed of light, and the collapse of time, so that there being no kind of progression of time in the propagation of the emission and the absorption events of photons being zero null separated, meaning that they're in the same point in space-time. Are there any implications for that, how we pull apart space and time from this different way of approaching the wave function?
Larry, I will answer that question in my second talk.
Okay, yeah.
You know, that it's...
But because I feel there's a lot of finesse. There's a lot of time is really, we try very hard to simplify time, and we know that it's not as simple as we think it is.
Okay, let's put it this way.
Could I say something?
Okay.
Could I say a little word?
Yeah, Nina,
yes, I would, a little.
Yes, you can carry on. Nina.
Yes. I like that you entered a velocity vector and got 3 vector equations instead of Maxwell equations. It's very, very interesting. And you got a very interesting solitons. But what about ball lighting? I think it is another nature, because the ball lighting is always moving and very quickly dissipate. But soliton is not dissipate so quickly.
Ball lightning lives.
Ball lightning.
Yeah, ball lightning lives for a long time compared to the duration of the lightning itself. You know, so, and of course it would dissipate because it would lose energy in the atmosphere. So,
maybe, but maybe
that
I know another another work about ball lightning with another what we say, I don't understand. Oh. What is this? I don't.
What's the problem, Nina?
Well, I don't understand. Peter asked me something. I don't understand.
Peter, did you ask something?
No, I'm not. Not yet, but I want to ask something.
Yes.
But coming back to ball lightning, to Laura's question about creating it, you can actually create it in a microwave oven. You know, I didn't believe this.
Grapes. Yeah.
With a grape in the microwave oven, and I actually did this. You know, I've got quite a fright of what happened there. You know, so especially if it was in a flat that I rented. You know, fortunately I didn't destroy the microwave oven, but
yeah, I was thinking in the discussion just now, ability to sustain some kind of form over some kind of period. So a lightning flash, a discharge itself, an arc, has like a average lifetime, an average time in which the ionization happens, whereas the phenomenology of ball lightning is that it persists for longer. So there should, that's something else that you should be able to show from the equations, that requires there to be something like in a traditional soliton, something that is self-reinforcing, that its dynamics with its environment tends to reinforce its structure, rather than it being a transition event, which a discharge arc is a transition event rather than a autopoietic form, if you see what I mean.
But look, the equation for the ball lightning, that I've shown, is that electromagnetic wave is just chasing its own tail all the time. So it is the only way that it can dissipate is by dissipating its energy. Which would be the glow, or in ionizing the atmosphere around it. So it's basically transferring its energy into ionization energy, which then gives us the light and of the gases. So it would dissipate all the time. And ball lightning is known to go through window panes. It's been known to go through an aeroplane. And bounced around and exited through the walls of it, So, but anyway, Peter, you wanted to.
Yeah, your approach is very generic and purely mathematical. So, if you've got three such starting vectors with those conditions, presumably you get Maxwell's equations for them, regardless whether it's E or B or whatever.
That's why basically that first part I use the vectors A and R, the activator, the reactivator. It's just a nice way of introducing it. I've actually written a paper just on that, on a purely mathematical generic form, and that's why I coined the term bimodal waves.
Yeah, so you should get Maxwell's equations for any system of that kind.
Of any, if you have a medium that allows this of two phenomena to be sort of that give you an induction. Yes, you will find it. If these equations can be utilized in liquids, like say a vortex or a smoke ring or something in that sort, I don't know. It's not.
Are you hinting, Peter, that we might see manifestations of the same thing in other contexts where?
Oh yes, indeed. Yeah.
Yeah.
Should we?
Well,
be able to generate such a thing, we should be able to see other manifestations.
Yeah, that would be interesting, because it might be that then you could find already in the literature or easily through some observations this same phenomenology emerge, which would be if the conditions for them. If it's rather elementary for the conditions for this kind of dynamics to arise, then it may arise not merely in the vacuum, but in higher analogues of the vacuum.
Yeah, in any system which obeys those conditions.
Yeah, and then we might, and I would not be surprised if we saw it self-similarly at different scales.
Correct, and basically on the one website that I monitor is this Quanta magazine, which is they worthwhile to register with them to get the emails of whatever they publish. And on the Quantum magazine, there is a very interesting interview with a Cambridge professor. Unfortunately, the name escapes me. But the one thing that struck to me is he said that fields, that the fields for the what you call them, the quarks, and the fields for all these components, he basically said that they are similar, to electromagnetic. He didn't call them electromagnetic, but he says that we have similar. There are always these two parts to it, like electromagnetism, that for the field. So basically this generic equation that I have there, I think is of utmost fundamental importance. And
so would you say even, would you go as far to say that it applied, because one of the things I have in my head is we have a notion of through and across variables, so conjugate pairs of two different variables that are often in the form of one is across and one is through. That could it be almost as general as that level of conjugate variables, where there is an ability for wave dynamics to arise?
Now, I think your understanding is greater than mine in this respect. I cannot answer that.
Yeah. Okay, no, that's an interesting thing, because that then widens the scope
it's true that all the forces have a Coulomb component, which means that they effectively have an E and B for that component, though they usually have another component as well. Two of them do anyway. There is a basic Coulomb component for the strong and weak, and of course for gravity.
Yeah. Okay. No comment.
Well, I know what I mean. That's well known. I mean, it's true. They have Coulomb components.
No. I don't argue with that point. I just I've got the advantage here of knowing some stuff that you don't know, which I don't want, which will come out in the next talk or in the next 3 series of talks. So, but now, if this is so fundamental, and now that you all understood this, can anybody suggest or tell me why I had no joy in getting this paper published anywhere? I always got these automatic rejections because I'm a Mr. Nobody without affiliation.
It's the same with all these things. That if you ever try to do anything fundamental and you're not a big name, then they will reject it automatically. You just have to publish it wherever you can. But unfortunately, that's the way it is. You can publish it in our, we're doing a special issue of Frontiers of Physics, so it might be possible to publish in that. I'm one of the editors of that.
Okay.
It's a special issue.
So, and when is the deadlines for this project?
There's no deadline at the moment. You can submit now.
To whom? To you?
But yeah, not to me. I'll tell you. I'll sort it out.
Anyway, if you can send me the email or email me with the links to whom I could submit this.
Yeah. I'm editing a journal with an issue of that, and I'm also editing another journal which it might be possible to publish in. I'm trying to think what it's called now. Symmetry. I'm also editing a symmetry as well.
Look, I think the one thing
Nature won't accept it. They never accept anything original now. They're only interested in Me Too papers.
Which group of Frontiers are you?
I'm with Lou and Torsten. We're doing the frontiers, and we're also doing the symmetry paper.
No,
I've already edited one. I think it's one symmetry.
Right.
And
My
we're doing the
question is
second
slightly
one.
different. Yeah, there you have categories in Frontiers of Physics, right?
Yeah.
One time wasn't you and Lou were going to write some paper in a sort of general section as opposed to symmetry or something. What was the?
No,
if
the Frontiers of Physics is the general one, yeah.
Okay.
But the thing is, you won't get into one of the very big journals because nobody ever does if they want to do anything original unless they're a big name. It's absolutely insane system. You know, because science doesn't work that way. That's big name. Big names usually come up with their discovery and then they don't do anything again.
But you know, what gets me is that, you know, I've got something completely fundamentally on mathematics, you know, with crossing over into physics.
Yeah.
You
I've been fighting the same battle for decades, and you know, it's the way it is. It's totally unacceptable, but unfortunately, that's what we're stuck with. And of course, fundamental physics hasn't advanced since 1973. Nothing really new that's any good has been published by all the, you know, in any of the big journals.
So the Higgs boson is moving the deck chairs on the Titanic, right?
No, the Higgs boson was 1964. Oh, okay, the experimental discovery is new, but the theory isn't new.
There's various the litany of failures is long at this stage, and supersymmetrical particles, etc., are not being found in LHC, and yeah, it's at the point where it's becoming sufficiently conspicuous that progress is not being made, that a lot of people are starting to question the way that the gatekeeping is being done, and that's good, but it just means that you do have to work and network with people to go outside.
That's the only way. That's why I've been asked to edit the symmetry in the Frontiers of Physics in order to try and encourage that.
It's institutional inertia that's the problem. It's
just disastrous.
The vehicles that should be carrying the project forward have become obstacles that are holding the project back, and unfortunately they have their own heft and weight to them. And
it's a perfect example of negative feedback. So you're not alone there, Anton. There's a lot of people out there screaming about this.
Now I've got one more. Look, basically, this paper that, you know, that is on the website, I already done that in February. You know, that Ron Whedon fortunately helps me with my English in the slot. And, you know, I submitted it to, I don't know how many journals, you know, within a day or two, I always get the rejection, you know, in other words.
Immediate rejection, usually.
It's immediate, it comes
immediate.
out.
Because they see you're not from an important institution, they've never heard of you, and you're trying to do something fundamental. Immediate rejection, no question. They don't even send it to a referee.
Yeah, correct.
Doesn't get to the referee, doesn't even get to me as the editor, so I've got to insist that I see them as an editor.
No. But anyway, there is one more journal, which is a mathematical journal, you know, which I just want to do a completely mathematical part of it. And this journal is, just trying to think of the name now. It's one that Ron Whedon recommended to me. They publish, I think, quarterly or half yearly, sort of a 6x9 format. And this is aimed at sort of university lecturers, you know, on basic mathematics and geometry and so on. So I might have a chance in there. Because,
well, good luck, but, you know, wouldn't ever build up hopes, but just keep plowing away at the foothills.
Basically, the website Harbingers of Neophysics was created out of this endeavor to get this out.
This is the reason why we got ANPA. That's why we had PERT and other conferences, and that's why. But there are a few things that are a bit more liberal than all that. There are some publishers that are a bit more liberal. If you want to write a book, and there's also, you know, some that some journals that are a bit more liberal. Only a few, but the famous ones are all garbage. They've produced nothing but garbage for years, except the experimental results. Only the experimental results are worthwhile. The theory after theory after theory after theory is a complete waste of bloody time. Supersymmetry, string theory, all that, total garbage, not actually addressing the real problems.
Are we done for today?
Yeah. Anyway, I'll talk to you about those issues. You can.
Peter, when are you away for your?
Next weekend, I go away for 2 weeks.
So
can we do it afterwards?
That's exactly what I'm. Next weekend is Thanksgiving in America. So you're away from the 26th and coming back on the 10th.
11th.
11th. So, okay, that means the next talk will then be the 17th of December.
Done.
Okay.
December. Unless somebody else wants to present something, I should advertise, so, you know, then. But that suits me very well to get the other papers, you know, into a presentation form and put it on the website.
Have you thought of publishing a book?
This is the next step, you know. It started off with a book. Then I thought, well, I actually wrote this paper hoping that to get it published as a sort of advertisement for.
But you won't get your book reviewed, of course, but you'll at least have published it in a book.
No, I will.
And you can get a reasonably good publisher for a book.
Correct. You can even self-publish.
Yeah, but you can do that. But you can also get a more established publisher as well.
No, they actually what I thought of doing is now what I'm going to do now. My plan of action is to put these papers down onto the website and then collate these papers into a book.
Yeah, it's important just to get it out there.
Yeah. And then once
people do write to you sometimes and say, this is fantastic. And you didn't even know that they were reading it.
So, you know, so that is my next step, you know, is I'll put it on here, discuss it with you, the feedback, whatever I get is valued and as such.
But it's a crazy system. I can't believe that it continues in the way it does. It's terrible.
There are other things in the world, not just in the stuff we talk about, which are crazy as well.
Absolutely, yeah. but you know,
Brexit,
we're supposed to be...
like the American elections and the war in Ukraine.
Yeah, awful stuff.
Correct, but you know, we've got look. It's post-truth was once a word of the year, you know, a couple of years ago. You know, that we now in a post-truth era. You know, what the hell does that mean? You know, and that people who's supposed to lead us can say, well, I've got alternative facts. You know, what are alternative facts?
I honestly don't know how people can choose to waste their careers on something that will never be productive.
But anyway, that's not for us to...
It is for us to say, because they're destroying the subject.
No, correct. So, but anyway, you know...
Anton, thank you very much.
Yeah.
I have to leave.
Yeah, Mike, thanks for joining us. And
see you on the 17th.
See you on the 17th.
And have a good trip, Peter.
Yeah, thanks, Mike.
Bye, Sydney.
Yeah, bye, Sydney.
Peter, is Lou well? He's not with us today, is he? I haven't heard from him.
Lou is traveling.
Well,
last week he sent me an apology because last week I had the introduction to this Harbingers of New Physics website, and he sent his apologies and said he's traveling, so wherever he is, he might not be at home at the moment.
Yeah, I think he was going to Dublin.
Okay.
Okay.
Peter, thank you. And
Thank you.
thank you very much for sort of reinforcing the idea that this is fairly fundamental and important what I'm doing here, you know, that you recognize it as such. It's interesting, Nina recognized, I sent this paper initially, you know, to Nina, to Keith Bowden, and also to what's his name, Alex Hinkie in India. And
Thank you.
all three came back with exactly the same comment. And it says, how can you introduce spin into this? Because then we've got particles. But that is what I'm going to do in the next talk. So thank you very much.
Thank you.
When can we look forward to the next talk, please?
The 17th.
Okay.
And basically, I think I'll just put out if somebody, I think next week is people in America are having their
Thanksgiving Day.
Fun?
Yeah,
Thanksgiving. So there's basically 26. So basically the 3rd and the 10th are open dates. I'm going to send out an email if somebody wants to present something on the 3rd or the 10th, then they must let me know.
Okay.
Oh, okay.
Yeah. Bye.
Bye. Thank you.
Thank you.
Bye.
Bye-bye. Thank you.
Goodbye.
Goodbye.
Take care.
Mm.